Hi, um, I need the phone for microphone purposes. Yeah, I'm not fancy. Okay, so let's put this whole delayed choice quantum eraser experiment mystery at rest once and for all. Because the big problem is that a lot of people have tried to explain it, and I always see that they kind of come up short. At the end, everyone is still, at least to some extent, confused. So let's this time just take it down to the simplest part that we can possibly do. So we're going to just use a simple diagram for the experiment, and that's it. Nothing else. No fancy animations, no fancy wavy interference patterns and all. So, what is this experiment? Let's just go through the setup, and I believe that explaining that is going to be crucial to eventually getting it right. So you see, from left to right, we start with sending our photons. So we send a laser through two slits, and after the photons have passed through each slit, then we use a BBO crystal. And so it's at that point that we actually turn each photon into two identical photons, near identical. Um, so basically, a parent gives birth to two photons. This is one of the important parts of it because uh, we turned each photon that passed through the slit into two photons. One of those photons goes up towards the D0 detector, and the other one goes down. So essentially, if we consider that there were two photons in the beginning, well, obviously there are a lot more. It's always statistical. Remember, with quantum mechanics, it's always statistical. So if we had two photons, one of them went down the lower slit, and the other one went to the top slit, bottom top slit. Then after the crystal, we will have four photons. Two of them will be going up, and two of them will be going down the diagram. And remember, to actually get the setup, remember that it has two parts after the crystal. The upper section, the D0 part, is one section, and the entire complicated setup at the bottom, that's the second part. So one of the photons that we created two after the crystal, with the crystal, one of them goes up, and that is the shorter route. So it gets there fast. Light has fixed speed, but it doesn't matter. At the end of the day, it's the shorter path, so it gets there sooner. So at D0, we actually find our photon, the first twin. We find it faster. But if you look at that image, you see nothing. I mean, obviously you see the light, but there's no pattern. The interference pattern is not there. So what's going on? We go down. If you look at the bottom part, what you see is that the photon goes there, the second twin, comes down, and then there are two different paths that it takes. So one of these splitters, what are these splitters used for? So they essentially are half-dim mirrors. So half of the light gets reflected, and then half of the light is allowed to pass through. So what happens is that the half that gets reflected comes down to one of the detectors that only is the path for it is only possible from one particular slit. But the other half of the photons that get passed through, they go through all the, crazy stuff. And at the end, they get mixed with the rest of the photons that are still in the path that come from, for example, if we consider that the photon that I was talking about came from the bottom slit, then they get mixed at the end with the photons from the top slit. And now I'm thinking, am I even pointing at the right angles because it might be here and I'm looking up there. Forgive the, all the elementary stuff. It's just the explanation that matters. So, yeah, we have all this. Some of the photons from the bottom slit will only go to the detector that there's only one way that these photons could have gone to that detector, and that's the bottom slit. And the same thing happens for some of the photons from the top slit. They can only some of them end up in a detector that they can only have come from the top slit. But the interesting part is that the rest of them will eventually get mixed up and be distributed into two detectors, which you don't know where they came from. So let's just talk about this a little. What do we mean? If you see the light at the detectors, I think it was 1 and 3. I don't remember the diagram. I don't have it. Sorry. The detectors I'm talking about, the ones that the path is known. So it can only have come from one particular slit. But the point is that in the other ones, when you look at the photon, when you look at the image, and remember, at this point in the experiment, if you look at all the observed photons, you see nothing. You see no interference pattern. There is no pattern. So if you look, but there's one thing. If you look at the detectors and the images that they took, that you don't know which slit the photons came from. Those images, well, you don't know where the photons came from. But the other ones, you actually do. So what's the point? Okay, we'll get to the point. Right now, run the experiment. Turn on the laser and let the whole thing happen. And all the light is absorbed at all the detectors. Finish. Remember, this is the crucial part that a lot of people get wrong with this experiment. And that is where everything is done and we're not sending anything else. We're finished. Now that we're finished, we go to the second step of the experiment, where we start to compare. So remember, at the top of the experiment, at the top of the setup, we had the D0 detector where a lot of photons went there, half of the photons went there, and they have the shorter path, so they always arrive sooner, always, than all the photons in the bottom. Then, after some time, other photons arrive. But we know exactly what the distances are, so we can calculate exactly how much delay there is. Okay, so if we look at all the 4 detectors at the bottom, if we look at those, we know if we, for example, see a measurement, one particular photon that led up the detector, if we look at it and then look at the time where it was observed, when it was observed, and we have the distances and we know the time delay, we can just calculate the difference, the time that it took, the delay that it took for this photon to be observed, and subtract that to get the time that its twin actually ended up there at D0. So we find the twin by time difference at D0. Okay, now if you start to compare these, like if you find all the twins from the upper part of the experiment and their twins at the bottom part, at all the 5 detectors, so 4 detectors compared with the upper detector. So if you do that, and if you overlap the results and you look at all the photons that happened at the detectors that the path is not known, when you overlap these measurements, you see an interference pattern. But if you look at all the photons and you overlap them, and you look at the photons the combination of the detectors for which the path is known and the upper detector, you don't see any interference pattern. And that's the interesting part of it. So you see, lots and lots of people talk about retrocausality, lots of people talk about all kinds of different mysteries that are going on here. But you see, there's not a mystery here. It's just this. It's just that you do the experiment. The setup is a little bit complicated, just a little. But when you explain it and then explain the fact that you do the whole experiment from start to finish, then you start to look at the results, compare them, overlap these things on each other, match them, then you see the pattern. And this is the interesting part. This is the fascinating part, and something that I don't know why a lot of people don't talk about often, because the interesting part of it all is they're temporally separated, they're spatially separated, and still correlated. That's the interesting part. That's the fascinating part. In time, they're different. They arrive at different times. They arrive at different locations, and yet they're still correlated. When you match the results, suddenly you see the pattern. That's actually very fascinating. And that's the part that, well, I don't see anybody explain. This is the experiment. And for all the interpretations that people have, it's on you. I'm not going there.